This is Shahul Ami, Professor ECE, Sedu Institute of Technology. In this session, we are going to discuss linear control engineering topic, Bode plot problem discussion. First, I will read the problem statement. Plot the Bode diagram for the following transfer function and obtain the gain and phase crossover frequencies. The given transfer function is g of s is equal to 10 divided by s into 1 plus 0.4s and 1 plus 0.1 s. So before solving the problem, we have to first substitute s is equal to j omega in this equation. When we are replacing it, then we get g of j omega is equal to 10 divided by j omega 1 plus j omega into 0.4 and 1 plus 0.1 j omega. Next one is we have to find the corner frequency in order to plot magnitude as well as phase graph. First, we have to find the corner frequency. So we have two corner frequency. One is related to this one, and another one is related to 1 plus 0.1 j omega. So first we have to take the low frequency and then high frequency. So I'm taking this one as first corner frequency, that is omega c1 is equal to 1 divided by 0.4, which is equal to 2.5 radians per second. Then I'm taking the next one is second corner frequency, omega c2 is equal to 1 by 1 plus 0.1, that is nothing but the coefficient of j omega. So the reciprocal of coefficient of j omega. So 1 by 0.1 is 10 radians per second. These are the two corner frequencies. Then we are going to find the slope of each and every term and also change in slope. When you are seeing the transfer function, we have three terms. One is 10 by j omega, another one is 1 by 1 plus j 0.4 omega, and another term is 1 divided by 1 plus j 0.1 omega. So first we have to arrange this term with respect to increasing order of the corner frequency, that is omega c1 is equal to 2.5 and this omega c2 is 1 radian per second, that is 10 omega c2 is 10 radians per second, and the corresponding slope of each term. Here when you are seeing the transfer system function, all the terms are in denominator, not in numerators. For each term, that is j omega, in the denominator we have to give minus 20 dB. So 10 by j omega, the slope is minus 20 dB. For this one again it is also in denominators minus 20 dB, and for this also, that is 1 by 1 plus j into 0.1 omega. For this also we are giving 20 dB. Now we have to find the change in slope in corner frequency. Here when you are considering the first term, there is no slope change. When we come to the next corner frequency, there is a small change in slope, that is we have to add these two terms, that is minus 20 is minus 40. This is the new slope for the corner frequency c1, omega c1. Now when we are come to next corner frequency, again the slope is changing. Now we have to take the new slope plus the second the slope related to the second corner frequency. So that is minus 40 minus 20, which is equal to minus 60. So using this table, we are going to find new slope, the exact slope of each and every corner frequencies. Now, so in order to plot magnitude graph, we need more number of points. Hence, we are taking low frequency, that is omega L, which is less than the first corner frequency. Here, this case, we are going to assume low frequency is 0.1 radian per second, and high frequency, which should be greater than omega c2, that is second corner frequency. Here we are assuming 50 radians per second. So we have four frequencies. For each and every frequency we have to find the uh, gain A. So let A is equal to magnitude of G of j omega dB. So A is equal to magnitude of G of j omega dB. Now we have to calculate gain at four different frequencies, that is omega L, that is low, omega C1, C2 and high frequency. First we start with the low frequency. Low frequency we assumed 0.1 radian. So we are going to find the gain. So gain A is equal to 20 log 10 divided by j omega. So we have to substitute, when you are taking magnitude of j omega, the same will come. So 20 log 10 by omega, the j will go when you are taking magnitude. So 20 log magnitude of 10 by omega. Now we are going to substitute the value of omega in this equation. We get 20 log 10 by 0.1 when you are taking log and multiplying 20, you get 40 dB. Similarly, we are going to find gain at omega is equal to omega C1, that is 2.5 radians. The same formula, A is equal to 20 log 10 by, directly we are substituting the value of omega in this equation. You get 2.5, you get 20 log 10 by 2.5, which is equal to 12 dB. Now when we are going to the second corner frequency, there is a change in slope. That is, we have to consider the change in slope, that is slope from omega C1 to C2. So at omega is equal to omega C2, the gain A is calculated by this formula, that is slope from omega C1 to C2 into log omega C2 by C1 plus A at omega is equal to omega C1. So which is equal to minus 40. This is minus 40 and omega C1, C2 is 10 and C1 is 2.5 plus this one is 12 dB, which is equal to, we have to calculate using calculator, we get minus 12 dB. At the same time, we have to find the gain at omega is equal to high frequency. We have considered 50 radians per second. For this, we have to consider the slope from second corner frequency to high frequency into log omega h by omega c2 plus gain at omega is equal to omega c2. Here slope from omega c2 to high frequency is 60. These things we have to take from the table. Log omega h, that is high frequency, is 50 and omega c2 is 10 plus A at omega is equal to omega c2 is minus 12 dB, which is equal to minus 54 dB. So these are the points and values related to magnitude plot. Similarly, we have to find phase of this transfer function. So here this is a transfer function, we have to find the phase angle of this transfer function pi is equal to, here the all j omega is in the denominator. For each j omega we have to give 90 degree, and if it is a complex number, that is real and complex part, then we have to take tan inverse of the imaginary part and the real part. So for j omega it is minus 90 degree, and for this 1 plus j 0.4 omega, we give tan inverse of, that is all are in denominator, so minus tan inverse of 0.4 omega, and for this minus tan inverse of 0.1 omega, because the real part is 1 and the imaginary part is 0.1 omega. So imaginary part, real part is equal to tan inverse of 0.1 omega. Now we have to find the phase angle for different set of frequencies, starting with 0.1, 1, 2.5, 4, 10, 20. So we have to substitute this frequency in phase angle equation and find the value of phase angle. For 0.1 we have minus 92, for second 1 it's around 118, 2.5 minus 150, 4 minus 170 degree, 10 minus 210 degree, and 20 it is around minus 230 degree. So we are going to use magnitude values and phase values to plot the diagram. So this is the plot. So first we will start with the magnitude plot. So here the frequency range is around 0.1 to 20. This is the range, and for this range the magnitude is around 40 dB to minus 54 dB. So maximum value is 40 dB and the minimum value is 54 dB. So I am just taking the left corner, top corner point is 50 dB, and for each unit I am giving 10 dB. So I get I am just mentioning the value for each and every division. So 20 and 0 is here, and I am drawing a line at 0 dB and it go up to minus 60 dB. Similarly, in the right hand side, for each and every unit I am considering 20 degree, and here also the range of degree is from 92 degree to 236. So I'm just starting from something around 80 degree, and each division is 20 degree, and it's go up to 240 degree. Now we have to mark the point, first point for 0, and in x-axis we have to take frequency. So I'm starting with 0.1 radians per second. So we know that each is decade, so each division is, you have to multiply 10. So 0.1 means if you are multiplying by 10 you will get 1, and then you have to multiply then 10, and it's 100 and 1000 and something like that, it's go. And here when you are seeing, you can find a lot of dark lines, 10 dark lines, 1, so 1, 2, 3, 4, something like that. And now we start with the 0.1. For 0.1 the amplitude, that is magnitude, is around 40 dB. So in this line 0.1 I am finding this is the point 40 dB, first point. Second one is 2.5, this is 1, and 2.41 is, this is 2, and it is should be in between 2 and 3. So this is the 2.5 point. So 2.5, the magnitude is around 12 dB, so it's above 10. So this is 10, and this is 12, so this is the second point. Third point is 10. 10, it's here, and so for 10 the magnitude is around 12 dB, minus 12 dB. So 12 dB must be below minus 10, so it's here. So this is 10, and this is minus 12. So this is the third point, and fourth point is 20 radians per second. 10, it is 10, the next one is 20. So 20, the dB is around 54, so 54 should be in between 50 and 60, so it's around here, so it's 54. Okay, so now we have to connect all these points using scale. So when you are connecting all these points, you will get this graph. Okay, this is the graph, this is the magnitude plot. Now we have to draw phase of each and every frequency. So for 0.1 radians per second, the phase value is 92 degrees. 92 degrees around, it's in between 80 to 100. Okay, 100, so it's around here. The next point is 1 radian per second. 1 radian per second, the phase angle is around 118. 118 should be in between 120 and 100. So above 120, this point is 120 is above 100, this is 120 is around here. And for 2.5 it is in here again, the same thing, 2.5, the value is 150. 150 is in between 160 and 140, the center line. So here this is 2.5 2.5 and 150. The third one is 4 is here, 4 is here, and around 170 is in between 180 and 160. So this is here, and 10 for 10 here, 210 is in between 220 and 200. So this is a point. Then 20 is here, and is here, and the phase angle is minus 236. It is in between 240 and 220, so somewhere here. So we have to connect all these points in freehand, so you get this plot. So this is actually phase and magnitude plot. Now we have to find the gain and phase crossover frequency. The gain crossover frequency, in that frequency gain value should be equal to 0. So when you are seeing magnitude plot, so this plot is crossing 0 line. So this is the 0 line. So it's crossing this line here. So we have to find the frequency. When you are seeing this, the frequency is around 5 radians per second. So gain crossover frequency is 5 radians per second. At the same time, we have to find the phase crossover frequency. In phase crossover frequency, the phase value should be 180 degrees. So this is 180 degree. So when you are tracing it, it is here, it's touching here. In that point, when you are seeing the frequency, this is also 5 frequency. For this problem, the phase and gain crossover frequencies are the same, or at 5 radians per second. Okay, thank you.